for taking the time to join this co-video conference, and this is the number 4 in our series, and I've titled it The Good, the Bad and the Ugly of 21st Century Exploration Geochemistry. This was a part of a presentation and a paper I gave quite a while ago, and I've just updated it a little bit as we've gone through. So an introduction a little bit to the movie for those that maybe haven't seen it or aren't familiar. It's a classic spaghetti western, and it revolves around some gunslingers competing to find a fortune of gold amid the chaos of the American Civil War. And this is not unlike our exploration cycles, both in budgets and commodity prices and the turbulence that goes on in that part of the world. And what was also known about this, what was also interesting about this film, was that it was one of the first to deal with really long shots, and this is the opening scene from the film, with very close-ups. And this reminded me a little bit of the scale at which we work in geochemistry, both at distal scales, regional geochemistry, and also the detail work we do on mine core, on drill core, for example. The film also has many stylized gunfights, which I would relate to the many tools we have at our disposal to do the jobs. And then there's an ongoing tension in the frontier, and that's not unlike the tension that we are accustomed to in terms of making that next discovery and doing things better. So there are 3 main characters. Clint Eastwood is the good as Blondie, Angel Eyes is the bad, and Tuco is the ugly. And these little snapshots will pop up on a number of slides as we go through the presentation, highlighting my interpretation of the good, the bad and the ugly of geochemistry. As I mentioned, this talk evolved from work that the late Peter Winterburn, myself and Dave Lowy did in an abstract that was part of Exploration 17 in Canada, and then it's also been published in the latest journal of GEA, which is Geochemistry, Exploration, Environment and Analysis, and that's available online. And it really picked up 4 main changes over the last decade or so, and those were understanding of metal mobility, rapid geochemical analyses, data integration, innovation in lab methods, and then there was a future challenges and frontiers aspect to the paper. And I'm going to go through each of those today as well. Now, this presentation is heavily biased towards my experiences and really in the regolith world, which is where most of my R&D exists. So for those of you that were hoping to see a lot of hard rock geochemistry, for example, with the Geochem, that's not going to be part of this presentation. And I'd like to acknowledge those 2 co-authors of this presentation, or the paper that fed into it. So that was MDRU for Peter, and Index with Dave Lowy, and also the Association of Applied Geochemists, for which we were all members and have been very supportive of me over the years, and have been an active organisation that I've been part of. And of course, I have to acknowledge the Hollywood film studios that I blatantly took screen captures of for their movie, and I don't acknowledge them anywhere else in this. So thanks for letting me take some of your imagery. But let's move into the geochemistry. And the first part was understanding metal mobility and mechanisms. And I guess in the 21st century, the good part of it is that we really have made an effort. And, you know, like this Cyanide and Happiness cartoon, maybe the effort is not quite been as successful as we would have liked, but we did make progressive steps in understanding metal mobility in weathered and covered terrains. And a lot of that came out of the Amara projects led by Ravi Nand and others, and people like Brian Townley at the University of Chile, and then MDRU has also had some of these type studies over the years for our North American counterparts in the exploration space. And what we really found was that this is when we started looking at if metals are moving through cover, how are they moving, and what sort of things can we glean out of the environment to inform the way we perhaps sample better And a really great example was actually visually identifying gold in this case, eucalypt leaves near the Kalgoorlie region. And you can see the concentrations of gold in these regions and how varied they were around the tree. And that informs the way we might sample. So because we did those studies, we then knew that, no, you can't just take a couple of handfuls of leaves. You really need to sample around the tree and get a representative sample. Likewise, we looked at gaseous mobility. We looked at microbial profiles in both the regolith and some of the groundwater characterization as well, and how those dispersion related to things like weathering a nickel sulfide body in this publication. We also looked at things like termite mounds, and much more detailed. So people have proposed termite mounds for sampling, and industry is actively doing it in many parts of the world. However, there wasn't a lot of studies where people have looked in detail about what part of the termite mound should you sample. Are all termite mounds created equal? And then studies like Aaron Stewart in this environment did that sort of research, and right down to the detail work where the image to the right of the screen shows the termites' kidneys, essentially the Malpighian tubules, and imaged the metal within the termites and how it's partitioned. And this sort of approach really showed the value of multidisciplinary teams, and we hadn't seen that so much prior to the 21st century. And this was a great example of that, bringing in microbiologists and entomologists, for example. The bad side of understanding metal mobility is that we really haven't adapted it strongly into our routine exploration. Things like regolith maps are very common, but they're not often actively sought after as almost the first thing you should be looking at. We haven't looked at mechanisms early on to maybe inform our best sample media and doing some of the, I guess, quality orientation work before applying it to a field site. The other thing that's probably the bad side of mechanisms work is around new techniques that have come out of the last decade or so with limited backup in terms of independent quantitative studies. And in this space, I would refer to the partial extractions and gas analyses, which I'll touch on later. In the partial extraction space, I like to group them into musical counterparts. So you have the classic artists, such as Beethoven here pictured, and you have the classic extractions. So partial extractions do include 4-acid digest, even though some may disagree. Aqua regia, malic is an agricultural extraction, and these are well studied. They're well understood how they work. And in the 21st century, we've seen a rise of, literally in this picture, the new kids on the block, where things like mobile metal iron, ionic leach, they appeared on the market and were being used. And some of them had a lot, they were quite popular, as were new kids on the block, but whether they stand the test of time, we'll wait and see. At the same time, when these were coming out, myself and my colleague Chris Stanley, who was visiting from Canada to CSIRO, had a little bit of fun at this approach, and we used household products such as red wine, Coke and Pepsi to do a comparative partial extraction test. And although this seems a bit tongue-in-cheek, and I liken this to Tim Minchin, who is also a Perth local, although living in the UK nowadays, I think. He's a comedic musician. However, what I wanted to impress upon is that there's also a lot of science or skill behind his work, as well as, and there's a bit of scientific rigor behind using perhaps red wine, because, and like Tim Minchin's classically trained musician, the red wine contains a range of different organic acids, and there's actually a chemical reason that we might want to use those as partial extractions. They have a whole host of organic acids that dissociate at various pHs, so they can attack the mineral surfaces, and they can also then form soluble complexes with things like copper and zinc and hold them in solution until we analyze them. So they make a really good partial extraction. However, what we haven't seen as part of the bad is the comparison of these studies with other things, and that's what myself and Cliff Stanley did early in around 2005 to 2010. And we actually compared a number of these extractions, and we don't see many of these studies. As a way to compare, we developed some statistics, which are really quite simple and easy to use to look at contrast, precision and accuracy in those responses. So this is only for orientation work where you know where you should expect an anomalous signature. And as you can see on the left-hand side, the wine performs really well. The grey zone, I'll just put the laser pointer on. The grey zone is the area where we expect an anomaly, and you can see a really prominent result there. The aqua regia worked, but it didn't work as well. And those error bars on there are bigger than they probably should be, and I'll talk about how good analytical labs are. I wasn't so good when I did the aqua regia in that experiment. But the benefit of doing the comparison is that you can then plot these and compare them. And what you see is in this figure on the right, as you head towards the apex, your extraction is getting better and better, both in contrast, your ability to pick up an anomaly, and also accuracy, your ability to target that zone of interest. And the wine performed probably the best of all of them. But some of the commercial and the proprietary techniques you see Genalysis listed there were also very effective in this setting. But we don't often see those comparative studies. For those of you that are interested in how we do that quantitative comparison, you can log on to Cliff Stanley's website, and I think he has an Excel spreadsheet you can download and do it. It's very simple technique. And we often see this, and it's really a good thing to evaluate traverses such as these ones published here. And this is really the ugly side of orientation work. And what we often see is these anomalies over mineralization, but we forget about all these nice things that sit out away from our area of interest. And rarely do they get explained, and rarely do they even get discussed. And I think that's a real ugly side of exploration geochemistry, where we haven't really focused on false positives, and there's a lot of work to do there. It's not sexy science, but it is essential for the future. And really what we've done is have a rose tint to our view of how well some extractions work and where they work. And this continues, the same author producing more of these sorts of plots here. And again, this was possibly relating to why things don't work. But again, these are published results and not just my own personal publications. And I'll just explain a little bit more about how that works and how we assess that, the ability to predict a mineralized zone. And this is the example from one of those earlier publications in the Journal of Geochemical Exploration. This is the actual traverse, and what it says is that if you assign 4 anomalous results in your traverse randomly along your number of samples, what are the odds that it's going to appear above your mineralized zone? And in this example, the odds of it appearing like this are about 2% chance. So you would have confidence that even though this is a pretty limited orientation work, this has successfully predicted the mineralized zone. However, what's interesting and what's often reported is we see results like this, where this sample is now a false or a negative response that you would expect, and people will report that as a rabbit ear anomaly. And to do that same calculation, all of a sudden the chance of generating that response is about 16%, and that's just by random numbers. So if you don't feel confident, there's a lot of the type 2 error, essentially, is the misclassification is poor in that example. However, that sort of plot is often published and put out there as a success without the rigorous statistical analysis. In another area of advancement over in the 21st century, we've seen rapid geochemical analyses. And this will come as no surprise to anyone. It's been a major change in the way we go about our work, particularly in field analyses, where you've got these handheld devices for everything from XRF, Raman, spectral mineralogy, all very easy to use, very easy to, and quite robust. You can point and shoot them at a lot of things. And then there's portable labs as well, such as the lab at RIB, which is a commercialized entity, but people are setting up their own sort of labs on field, on quite portable and at field sites. And that's been really good. And one of the demonstration in my own work has been where, with the Geological Survey of South Australia, we were asked to characterise a really large area, 4,000 square kilometres, that was really remote, and also we didn't want to have a high impact, so we wanted to get in and out of there quite quickly. So it was a helicopter-based survey, and what we were able to do by using the technology at our disposal, so this is again free applications that you can put on your phone, or in this case it was on a little tablet, and you can rapidly record location, sample type, regolith position, a range of different data very quickly while you collect samples. And we're scanning QR codes, and it was all integrated and backed up onto a mobile server, and then also ingested at the end of the day. So we were quickly pulling that data off and being able to work with it. This is published in both open access sites, both the MESA journal and the Explorer from earlier this year has some of that information. Explorer is the newsletter for the Association of Applied Geochemists, so you can find that on their website. Just behind that rapid sampling, we also had one of these portable labs where we were setting up in the field, and we were getting results within, well, in some cases, less than a few hours behind the sample crew. The benefit of that was that we were able to, one, prep very effectively. There's now mobile mills and crushers splitting. You can see to the right, bottom right of screen, there's a little puck press and producing a really good quality sample for the analysis. And then we're doing portable XRF and spectral analysis on that. So what we were able to do was produce geochemical maps as we went along. Now, that was incredibly powerful as a demonstrator of how you might go about infill sampling on the fly. So not only not having to remobilize a team a month later or 2 months later once you've got your geochemical results back, you can actually do that while you're out on site and then say, well, let's close the spacing in on this target. And we did that from 4 kilometre spacing down to 1 kilometre spacing in this zone of interest. The bad side of this is that detection limits for a lot of the elements of interest are still a challenge with portable XRF devices and many of the other handheld devices. And this was our map of that same region for copper. There's no information there whatsoever. This is improving all the time though, so it's bad at the moment to some extent, and it's just one of those limitations we have to work with. However, there's things like the detector technology that came out of CSIRO that's now part of PPPB, and that's an ability to use portable XRF and get parts per billion gold in the field. There's a couple of steps involved, and it's maybe a few days behind, but it's not months behind the analytical results. And then there's the ugly side of the portable devices, and that's really around partly our own fault because they're almost too easy to operate, and anyone can press buttons and get data. And that's been a real challenge because good operators are still really essential. Good quality training, I would definitely endorse for all these devices. And even in a situation where, you know, we were somewhat well trained, and this is that example in South Australia, we were sampling this, and this is one of the results from the geochem that we were generating. And what we realized was that there was this, what looked like a really big anomaly that matched up with a big magnetic anomaly underneath. However, what we found was that the standards that we were running during the day, on those 2 days of sampling, we were using a mylar film. On other days, we were not using a film at all. And so it had skewed the results. And when we reassessed them, that was our result, and it was much different. And that was with people that would consider themselves pretty adept at using portable XRF. So it can happen to anyone, but it's really something that we need to be cognizant of. The other side of the ugly, I think, is the way people deal with non-normal distributions and closure in data. Again, closure, probably more of a lithogeochem, whole rock sort of analysis type issue. It does pop up everywhere though. And it's often ignored. And for those of you that are really interested in how to do this better, central ratios are a really quick and easy step. But you can look at the paper, and this is an open access paper that's been published by Geo from Eric Grunsky and Prix to Caratat, and that covers that issue quite well. The next stage is around data access and interoperability, and I think people would be really familiar with the big data concept and how much that has changed in the 21st century. Our compute power is bigger and better than ever before. We're able to just do a whole lot more. We can run more models, we can run different processes almost continuously, and the flow on benefits from exploration into the processing side and potentially back are there. There's the ability to integrate and use multiple data types together. So this is evaluating spatial data, geochemical data, and geophysical data together. And we can do this from perhaps our interpretation of our results for targeting. We can also do this to generate models for smart sampling. What are the minimum number of samples you need to take to get the information you need? And all this is because we can generate models with uncertainty. And so you have numbers backing you up in your assessment. And so rather than looking at perhaps your geology map and your gold concentrations and saying, oh, I have a gut feel that we've done a good, that's an interesting area, but it hasn't come up, you actually have an uncertainty number where you can say, we've undersampled that region, perhaps we need to go back. And that's really powerful. There's some good things coming out of that. The bad side of it is that we don't always follow what we know. And I use this example as the exploration money pit and assuming we have a $5 million budget for perhaps shallow drilling in a remote area. And one of the first things that comes into play is let's reduce the budget by 10%. It happens all the time. And people's instinct is almost, well, we've done this, we've got to do this much drilling, let's save that money by cutting our analytical costs. And I've modified an example from Nick Oliver's short course here, where you see that essentially a $600,000 saving by cutting your chemical analytical costs from maybe $60 to $45 a sample. But what's not recognized is the biggest cost there is actually collecting the sample. So in the regional, this could be drilling, it could be soil sampling, that it doesn't really matter too much. But the way to really adjust your save money is not doing that, because by not cutting your analytical costs, because what ends up happening, you make poorer decisions based on poorer quality data. How you can save a lot of money is just by cutting the number of samples. And you can do that really quite easily with the big data and with the other sort of smart sampling approaches that we can do. And it's a bit of a challenge, because probably with saving that 50% of cost, you may have to engage some consultants or an R&D company or a different group of people to set up the machine learning approaches in this case, where it does still pick out the anomalies of interest. You can see the same zones could be targeted, but you need to engage the right people. And there are a lot of smart people out there that can do this type of thing. And it's not just for regional drilling or sampling, it could also be for your analysis downhole. So this is a really quick way to improve your budget, and not by shortcutting on the analytical space, which I've seen is one of the bad aspects of exploration geochemistry. The ugly side sort of links into that a little bit too, where it's about the culture with grid-based sampling. It looks good, it's traditional. We're often the budget is approved for X. It might be in that case 300 holes across a region, but turning around to your manager and saying, I don't want to do 300 holes, I want to do about 150 to 200, but I need to engage some machine learning smarts and make a way to do that better. That's often hard to do and hard to adjust budgets. And people, when things are going well, people are often too busy to improve. That's another challenge we have. You don't have that headspace or the leeway in your work program to stop and redirect or look at how you can do things better. And as I mentioned earlier, we still often evaluate numbers separately. We still tend to drill the biggest numbers, and we don't necessarily follow up on things like those false positives or subtle anomalies that may stand out better if we looked at all the data together. And when I wrote this, data sharing was another area that was really, I guess, a poor part of exploration culture, where companies weren't prepared to share data. And in just the few years since we did this, I've seen a marked change in that area. The unearthed type challenges where companies have given their data open access to the community have been a really eye-opening experience for many. And I think companies in general have become much more open about data sharing, which is really valuable. Innovation in the analytical space is something that I work in quite regularly, so I'll spend a little bit of time on this. And really over in the 21st century, instrumentation has got better and better. The labs are absolutely top level in terms of their output, the way they go about things, that, stable extractions and analyses, multiple elements are standard now. Isotope analysis has become more accessible as well and of better quality. So those things are big improvements too over the last decade or so. Element mapping, I'll spend a little bit of time on this because it's a really significant change in the geochemical world. I'm not going to talk too much about the Maya maps and techniques. Our next co-video conference in 2 weeks' time will be a walkthrough of a range of different Maya maps and what they tell us about their samples. And that's going to be a number of staff from CSIRO presenting that work. So I won't spend too much time on that. And then there's the next generation of workflows. And this is where I do think things will improve they're improving now and they're going to improve in the next decade as well. My personal work is in ultrafine clays and soils and using that technique, but it's about pairing up multiple data types together and giving access to that to the industry. And I'll come back to that in a minute too. And it's really about picking the best methods for the jobs required. And, again, I've pinched a little bit from Nick Oliver's short course here and modified it. He talks about pairing the right instrumentation with the right analytical method for downhole geochemistry and lithogeochemistry. That makes perfect sense. And I agree, we should be aiming for George Clooney's Corvette in most cases, but it's not just the digestion or the instrument. It also comes down to what sample media is best. And in my view, often we've stuck with a standard less than 250 micron, for example, when maybe we should have looked at alternatives. I like the fine fractions, but in some cases in the settings, the coarse material is really effective. And again, it comes back to understanding heterogeneous samples versus consistent and controlled media and what works best in your settings. And if you mix those up, well, things don't work very well either. And I would argue that in many cases, we've spent a lot of time over the last decade, with George Clooney in his smart car here or the mini equivalent. It's okay looking, but it's not as good as we can do, and we can do better in a range of ways. And that's where we are at the moment with the current best geochemistry is the George Clooney's Corvette. But what I mean when I talk about the next wave of workflows is things like the ultrafine technique, but there are other options where you not only get the standard geochemistry, so your multi-element data, but you also get additional information. With the ultrafine, you get things like pH, conductivity, particle size distribution. And, I liken that to Leonardo DiCaprio here in his sports car. But then you can also package in things like spectral mineralogy, and this is incredibly powerful. And I've got Justin Bieber there with his Lamborghini. And the reason I've chosen the Bieber is because, for maybe some of us older geochemists, and I put myself in that group, we're not as comfortable working with spectral mineralogy and geochemistry together. But I think the next generations will become very comfortable with these large data sets and work almost seamlessly with them. And they get Justin Bieber. They know what that's about. And I think we'll know much more about the value of a spectral mineralogy being incorporated with our geochemistry. And I think as a whole, industry should be almost demanding that they're getting these extra value add-ons to their samples. As I said before, don't shoot yourself in the foot by cutting corners on your analytical extractions. You're better off getting all the data and making better decisions on less samples. And these workflows go along with that same sort of mentality or approach. Instrumentation for viewing samples and geochemical mapping has come along in leaps and bounds. I mean, it was improving massively in the early 2000s. You know, this is just field and mission gun SEM work here of gold particles, and you can see zoomed in on this gold triangle. You see another population of gold triangles that's smaller amongst some halloysite rods there. And then you zoom in again at 20 nanometer scale bar here, you're still seeing gold triangles, and you're seeing another population of what looks like gold in the background. So we're able to image that sort of information that we were never able to see before. This was invisible gold that we're now able to clearly depict with the instrumentation. Laser ablation, ICP-MS, is another technique that's become much more used. Here's an example of one of my samples, and nothing really exciting to show here, but you can see as you go across, the traverse runs across there, and as you hit this little dark blob, all of a sudden there's a change in the chemistry. There's an increase in iron, there's an increase in nickel and lead, a little bit of sulfide or something like that. And there was a presentation at a webinar yesterday from UQ, and Sean Barker out of Codes presented some of the value of laser ablation, and some of my colleagues in CSIRO are also doing a lot of work in that space. And the information it can tell you on detailed mineral maps, essentially, or chemical maps. On pyrites is an area that Codes have worked on extensively. But one thing they haven't necessarily covered, and one of the challenges with laser ablation, is you can only cover a smallish area. But things like the Maya maps out of either the Maya detector in the synchrotrons or the Maya mapper, which is I guess a smaller version of that, and not quite as good a resolution, is that you can see things on a much bigger scale. And I haven't got a scale bar on this image from Mark Pierce, but as an example, the stuff you would see on a laser ablation might be this little, it could be this little pyrite grain here in green. I'm not sure what the color scheme is in this map. And that will tell you, perhaps looking at the arsenic in that pyrite grain, about, you know, the alteration that grain has been exposed to, and maybe the gold distribution, but it may miss the gold distribution that's through this calcite vein, for example, where there's a whole other story that we're not seeing because we're focused on something very detailed. And so our ability to map at different scales has really changed the way we look at our geochemistry and our processes as well over the last decade. And that's not just in 2D, you can see things in 3D. And here you have a micro XRCT from Linda Godel, and I can't remember where that was published, but you can look up her name and you'll find that article quite easily. But what that is I think it's a magmatic rock, and looking at the chromite and I think the nickel and platinum distribution within that core, but you can rotate it in 3D and get information about how those are distributed. XRF mapping on the desktop can be very quick and rapid, and here you can see at the top is some uraninite ore going into the host rock, and a rapid change from uranium-rich rocks. I can't remember, there's little garnets in there, into some silica-rich rocks there. And it's a good way to look at your geochemistry and then pick your areas that perhaps you want to do more detailed work on. And again, here's another synchrotron map which talks to us about process, and this is the DeGrussa copper gold sulfide deposit, and this is the regolith just above that. And what it was showing us in the mechanistic studies was that things like copper and arsenic were in the matrix, so they're these purplish colors in the bottom of this image. So they were being dispersed through the regolith, whereas the gold itself was as tiny little particles all through the regolith, but very small, discrete gold pure particles. And that was telling us a little bit about the processes that were going on there. And we wouldn't have been able to see that without this type of technology. The other thing that's really evolved, and again, this is not necessarily geochemistry, this is mineralogy mapping now on the AutoGeo SEMs, like the TEMA, for example, here. And this is one of our exciting developments coming from the team led by Adam Barr, is that not only are we able to do some great work with the TEMA mineral maps, but the desktop libs device now, we can get maps not as at the same quality, but we can generate things that we're doing in 2 hours plus sample prep time, which took a lot. We can generate roughly with no sample prep and about 90 seconds of analysis. The data manipulation and the number of other parameters are really challenging in this space, but the technology is coming, and I think we'll see this presented in the next decadal advances in geochemistry. So very exciting sort of results coming out there in mineral mapping as well as this chemical mapping. The bad side of the analytical space is that there's more black boxes, and these tend to have biased evaluation, which is a real challenge because there's not a lot of contrasting studies where people look at multiple either extractions in the partial digest, but in soil gas analysis, there's not a lot of independent studies where people have said if you're weathering this type of sulfide, you should see this gaseous signature. And so what we tend to get is results where the industry doing the gas analysis actually ask for your sample locations because they'll plot up some sort of map, and it often looks like this thing in the top here where, yes, you've got an anomaly, and it's biased because it's most likely that you're going to do an orientation survey and put your mineralization somewhere in the middle of your survey. And so what I did with that same data set without knowing anything about the gases involved, I just took anything that had an elevated signature somewhere in the middle of the traverse and multiplied them together. And you can see this is actually published. You can see the pattern in that geochemistry matches quite similar to the stuff that was reported. But again, without those independent studies, it's really challenging to know how we progress this. And CSIRO's Chloe Platt is doing some fundamental background research on soil gases at the moment to try and get to that information, but it needs a lot more work. The other thing that we've done badly is we've been forced to explore through cover, and that's no secret. But one of the bad approaches we've done too often is we explore through the cover like there's no cover. So we just do 4-acid digestions on sand dune material because we did 4-acid digestions on residual soils in the adjacent 50 kilometres where we were working. And again, we haven't really stopped to think about perhaps maybe we need to treat this cover differently and need to think about what the cover actually is. And in sand dunes, for example, there's no value in digesting the 95% silica dioxide that's in there because it doesn't even tell us any information about like the provenance of those sand dunes. We don't really care. What we're interested in is there anything being mobilized from below and coming up through that environment that we can detect, perhaps base metals or gold or something like that. And if it's moving through there, and I've got other presentations and publications around this, it's likely to be small, it's charged, and it tends to be on the finer soil materials. So this is the clays in particular and iron oxides, and you can see that in this example here where most of the gold was on that material. So we should be looking at why are we analysing the bulk material? Why aren't we refining our techniques for exploring through cover better? And the ugly side of this is sometimes we get really poor reproducibility for gold analysis. And in this case, doing a standard analysis of, I think this was Aqua on a -180 micron sample for stream sediments, produced this type of reproducibility for gold. And this was a large geochemical survey in the Yukon. And essentially what it did was give very little confidence to industry that they could use the gold data. And it delayed opening up a really prospective terrain, such as the white gold region in the Yukon, that didn't really come to the forefront for another 5 years with the discovery of the coffee deposit. But you can see that reproducibility was terrible there. However, if they'd done some of the orientation at the front end with the gold in particular, the other multi-elements were okay, they could have refined the technique and got better quality data. And this is what Dennis Arne and Bill McFarlane published in the 2014 Explore. They took some of those same samples stripped out the finest fractions, in this case the clays. They also did legs and a couple of other things for comparison. And what they found was they got really good reproducibility with that fine material. Now, if the survey had done that orientation work early, they could have produced a fantastic data source for gold in the Yukon in 2003. And QAQC is what comes down to being the most ugly aspect of exploration geochemistry again. And this is Peter Winterburn's example where he was comparing two different sets of data with a water extraction and couldn't understand why there was such a difference. And it wasn't until he went back to the lab that they were doing things, even though it was a deionized water extraction, you would think it would be pretty standard. They were doing them at two different temperatures, and without checking and doing the QAQC checks, he would have got really skewed results. And you can see that as the temperature increases, your solubility of many salts increases, so you're going to get greater concentrations. And that's exactly what that plot shows. And now to the future challenges. As I mentioned, undercover exploration, it's widely discussed both in Canada, Australia, Chile. There's large tracts of land that are undercover and need to be explored. How do we do that better? This is both good, bad, and ugly in many cases. One of the things that's a good aspect, and that I think people haven't recognised, is a lot of the plots that show, you know, the depth of discovery is becoming much deeper and deeper, are heavily skewed by a couple of results. And when you filter out those results and look at median values and stuff, and Mark Arundel gives a really nice presentation on this called Value in the Shallows, what you can actually see is that the average depth for gold discoveries globally is only around a metre of cover or a couple of metres of cover. And for base metals, it might be only 20 metres of cover. So there's a lot of opportunities in fairly shallow cover that we haven't necessarily embraced. And so developing techniques for that depth of cover is valuable, as well as the really deep techniques, which probably geochemistry is not as well attuned to. You need to look at maybe interfaces and some other things. The state of the geochemical nation. Now, this is another area that is in a bad state in many ways, and one of the reasons is the economic cycles and retrenchments. And this was written a couple of years ago, but probably quite pertinent now as well. Is that when things go bad, we often lose the middle tier of our industry and the middle in terms of experience and their positions. So when things improve again, we rehire junior staff, and the senior guys tend to be in less hands-on roles. So there's this missing gap, and that shows in the loss of knowledge and experience, and we tend to reinvent the wheel on a number of sites. And I've seen this firsthand with training courses at company sites where we'll talk about results we did for work on their site not less than 5 years ago, and people won't know about it, or maybe it's a few more years than that. But we're losing that knowledge, and that's slowing up our ability to explore better. Also, because of these sorts of changes in the industry, the middle tier often go into consultancy type roles. So while that's really valuable in terms of getting good results quickly, as consultants tend to do, there's not a lot of knowledge transfer in using in the consultancy space. There is some, but it's not as great as it would be had industry maintained, I guess, that middle tier of staff, and also had R&D and the university sector continued to have quite a broad number of staff as well, and that's declining quite rapidly as well. So there's not a good supply of young academics in geochemical research, and that is going to be a real challenge for the industry going forward. And then finally, research support from industry, and this is certainly good, bad, and ugly. We see there's industry that is open to supporting research. They fund it, they collaborate, and this really is our lifeline for industry, for people like myself and CSIRO and other organisations around the world. And the other thing that's really good in Australia, and I know this also occurs in Chile, and I'm not sure if there's an equivalent in other parts of the world, but there's an R&D tax concession for industry. So in many cases, the work that's sponsored is 40% tax deductible. Now, that's not just the cost of maybe doing the project, but, and this is where the bad part comes in, that R&D tax concession is not always considered. And so because one part of the industry funds a project and another part is reclaiming that tax concession, they're not looking at the net gain for their organisation across the whole. So that often doesn't get considered. And a really good example I've seen quite recently, the R&D tax concession covers, in some cases, analysis of samples in the field, but people were maybe going to do something similar anyway. And because they haven't engaged with the R&D project, they can't claim the other samples. So they end up losing money because they don't do the project. So that's a bad part of it. And that's partly on industry, but it's also partly on researchers like myself, not perhaps explaining how the benefits of those concessions and how they can be realised. And also industry tends to expect a lot for a little in research space. And you know, the return on investment, I would argue, is pretty good for most research projects. But when you compare that to the return on investment for exploration success in general at around 1 to maybe 5% if you're really good, the return on investment for research looks pretty good, I would argue. So hopefully people will keep that in mind when they're looking to fund future projects. And then the ugly side is where technology and IP has been used without credit. And this has not affected me personally, but I have seen it where researchers have had their ideas commercialised and taken without any credit whatsoever. Not necessarily wanting a financial return, just wanting the credit. So that's the ugly side of some of the R&D support. But overall, it's pretty good. And we'll finish up going through how the movie finishes with the ugly, you know, that we've talked about quality control for samples, the rose-tinted glasses when looking at our anomalies, and particularly the demographics of our geochemistry colleagues in general. The bad, hopefully it ends up like Angel Eyes in the movie, dead and buried. Black boxes without comparisons, we really need to change that approach. We need to be much more open about what things are doing and how they're working. The short-term outlook isn't very beneficial for things like larger scale mechanistic studies. And then the big one is around cutting analytical costs instead of samples. I think we can do much better by not cutting analytical costs and cutting our number of samples. And then there is a lot of good that's been made over the last, in the 21st century, in particular the last decade. And that's been around making progress in the mechanisms. Data sharing has increased markedly. Rapid and mobile technology continues to advance, and particularly the geochemical imaging side as well. And so there's a lot of exciting things coming out, and that will help us find, you know, the future Confederate gold, or as in the movie, or our other exploration targets. And with that, I'll ride off into the sunset and answer any questions that you may have. This presentation has been recorded, so we will release that in probably a week or two, and you can connect with me on LinkedIn because I tend to post those when they come out there, but look out for them in other platforms as well. Thank you.